Now we're going to introduce a couple more definitions for this section. These definitions, though, are rather simple, and we'll be able to get a quick sketch of how each of them tends to work with the pictures over at the right side. So we'll say here that a sequence is called bounded above. It's bounded above if there is a number, we'll call it capital M, such that all the numbers in the list A at all possible spots are less than or equal to M for all the different n values in the list. Now, this value of M is called an upper bound for the sequence A sub M. So we'll kind of see what this looks like. I'm going to go ahead here and treat M as a red value that I can draw here in a picture. And let's go ahead and just put in a hypothetical sequence. Let's say I have a sequence that looks something like this. Maybe it goes up and down and moves all over the place. But if I had a sequence that looks like this, I could easily go ahead and see that if these were the only dots in the picture, I could definitely state that this height right here is a number that no dot in the entire sequence is ever larger than. And so this makes it a upper bound for the sequence. And I can say that the sequence is bounded above. It's a cap. It only gets so large. In a similar way, we could say that a sequence can be called bounded below if there is a number, let's call it little m, such that A sub n would be greater than or equal to little m for all n values 1 and greater. And that would make little m be called a lower bound for A sub n. So pictorially, this would look like, well, maybe I have a sequence that goes something like this. Maybe it even continues to go up and up and up forever after this point. But little m, which I'll draw here in blue, could just be some value for which no dot in the sequence ever goes below that line. That's it. Now, we could imagine that there might even exist a sequence that has both of these properties true, that when I put in like all of the different dots, maybe there's an M, capital M, that bounds it above, and there could be a little m that bounds it below. And if that exists on a sequence where you can say that all the dots never get bigger than some value, and all the dots never get smaller than some value, then we say that that sequence is bounded. So we say that a sequence is bounded if it has an upper and lower bound. That's it. Now, we'll see here in example number 3 how easy this can start to be to show. Take a look here at this sequence. It's 6 plus 1 over m. And I want to show that this is a bounded sequence, which means I'd have to show that there's a red m, some value where nothing in this list could ever get larger than, and also little m, some value, any value, that these values cannot get below. I'm actually going to start with the lower value here because I think it's so incredibly easy. Notice here that if n is going to be, again, a number 1, 2, 3, 4, 5, 6, on and on, then is there any way that any number in this list could, say, be smaller than 0? Is that possible? Could I ever get a negative result out of this? No, absolutely not. So I could say that we could see that A sub m is definitely going to be greater than 0 for all values of n. So 0 is a lower bound. Notice this isn't the only lower bound. Couldn't you say that this sequence is never going to produce a number that is smaller than 2? Because it's always 6 plus some positive amount. So it's important to note here that this value that I found here for m isn't a unique value. I just am looking for a possible value. Well, notice I could say the same thing then by looking at upper bounds. Let's see. Is there a number that I could guarantee no number in this list would ever get larger than? Well, let's see. I mean, couldn't you definitely say a sub n is always going to be less than or equal to 7? Since we know that 1 over n is always less than or equal to 1, right? Like if you plug 1 in for n, you get 1, but anything else you get smaller. So the biggest this could ever be is 6 plus 1. So 7 is an upper bound for a sub n, right? I found a possible red value. Notice again, that's not the only red value. I could also say 7,000 is an upper bound because nothing in this list is going to be bigger than 7,000. But now I can easily see that a sub n is bounded. Now the question might be here, why do we care about all these different pieces of terminology? Why are we looking at increasing and decreasing, bounded and bounded above, bounded below? Why does that matter? What does this have to do with integration in the first place, the whole reason we're here, but also what does it have to do with the idea of doing limits of sequences? Well, we'll talk about that in the next video.